You know when someone says their AI model is 99% accurate? What does that number really mean? And is it even the whole story? Well, it turns out there's a whole mathematical universe behind that single number. So today, we're going to pull back the curtain and build that framework from the ground up so you can truly understand how we measure AI performance.
Here's our roadmap. We're going to start with the absolute basic unit of machine learning, a single prediction, and then we'll build on that, piece by piece. By the end, you'll get the elegant and sometimes kind of tricky trade-offs that go into taking a model's super complex behavior and boiling it down to just one meaningful score.
All right, first things first. Before we can even talk about scores or grades, we need to have a shared language. So let's get super precise about what a model or an AI system is actually doing at its most basic level.
So in the world of machine learning, we often call a model a hypothesis, and we just use the letter H to represent it. Really, just think of it as a simple function. It takes an input, which we call x, and that could be anything, an image, a sentence, a row of data, and it maps that input to an output, which we call y. For example, if x is a picture, our hypothesis H is the rule that looks at all the pixels and then spits out the label y, like cat.
Okay, so our hypothesis H sees some input and makes a prediction. Great, but was it a good prediction? Was it right? To answer that, we need a scorecard. We've got to have a way to assign a number that tells us exactly how well the model did on that one specific example.
And that scorecard is called a univariate utility function. Now, univariate is just a fancy way of saying it looks at one thing at a time, in this case, one single prediction. It takes that prediction, compares it to the actual truth, and spits out a number. It's kind of like a judge at a diving competition holding up a scorecard. And the most important rule here is super simple. For a utility function, a higher score is always better.
Now, to build these scorecards, we need some tools. And one of the most fundamental tools in the box is the Heaviside step function. It's really just a simple but super powerful on-off switch. If you feed it a positive number, it outputs 1. If you feed it a negative number, it outputs 0. And what if you give it exactly 0? Well, it gives you a half point, which is kind of like the mathematical way of saying, I'm not sure.
And just look at this graph. It shows you exactly why this thing is so useful. You see how for every negative input, the output is just a flat 0? Then bam, right at 0, it jumps instantly to 1 for all the positive inputs. That clean, decisive leap makes it the perfect tool for scoring things that have a clear right or wrong answer.
So how do we actually use this? Well, let's build the most common metric of all, accuracy. Imagine our true labels, our y, are either +1 for yes or -1 for no. Now, if our model's prediction, h of x, has the same sign as the true label, what happens when you multiply them? Their product will be positive. You feed that positive number into our Heaviside switch, and boom, we get a score of 1, correct. But if the signs are different, the product is negative, and the Heaviside gives us a big fat 0, incorrect. It's really that straightforward.
But think about it. Is right or wrong always enough? Sometimes what we really care about is the order of things. Like in a search engine, you don't just want a list of correct results. You want the absolute best result right there at the top. This is where we have to move beyond scoring just one prediction at a time.
And to do that, we need what's called a multivariate utility function. All that means is that it looks at more than one data point at the same time. So it might take a pair of items, say 2 different emails, and instead of scoring each one individually, it asks a different question. Did the model correctly give a higher spam score to the email that was actually spam?
The concordance indicator is the perfect tool for exactly this. It takes 2 data points and it compares the order of their true labels to the order of the model's predictions. If the orders match up, we call that concordant, and we give it a score of 1. But if the model got the order wrong, we call that discordant. It gets a 0. Simple as that.
Now, here's a really clever trick. We don't have to compare every single possible pair of data points. We can restrict the domain, which just means we only focus on the pairs we really care about. For instance, maybe we only care about comparing a spam email to a non-spam email. And this seemingly small step is actually the secret ingredient to building one of the most powerful metrics in all of machine learning. And we're going to come back to that. Okay, so we know how to score a single prediction or even a pair, but that's not the holy grail, right? What we really want is that one single number that tells us how the model would perform on average across every possible piece of data that exists or could ever exist in the universe.
This ideal, absolutely perfect score is called the Estimand, and we represent it with the Greek letter theta. Think of it like this. If you wanted to know the true average height of every single person on Earth, the estimand would be that one true number.
But of course, you can't go out and measure everyone. The estimand is our target, the ultimate ground truth of our model's performance. The only problem? It's impossible to ever calculate because we never have all the data.
So if we can't know the true score, the estimand, what do? Well, we do the next best thing. We try to estimate it using the limited sample of data that we actually have in our hands.
Okay, this right here, this is probably the most important distinction in all of performance evaluation. The estimand is the mountain peak we're trying to see. The estimator is the telescope we build from our limited data to try and see it. So every time you calculate accuracy on a test set, you're not actually measuring the truth. You're using an estimator to make your best possible guess at that truth.
So our estimator gives us a guess, but how good is that guess? Is it reliable? You know, this question leads us straight to two fundamental ways our guess can be wrong, and they are almost always in a constant tug-of-war with each other. On one hand, you've got bias. Think of this like a scope on a rifle that's misaligned. Your shots might be really tightly clustered together, but they're consistently hitting off to the left of the target. A biased estimator is systematically wrong. Then, on the other hand, you have variance. This is more like having a really shaky hand. Your shots are all over the place. Maybe they're centered around the target on average, but each one is imprecise and totally unreliable.
And here's the really beautiful part. The total expected error of our guess, what's called the mean squared error, can be broken down perfectly into these two components. It's just the bias squared plus the variance. And this isn't just some neat math trick. It's an incredibly powerful diagnostic tool that tells us why our measurements might be wrong.
This table puts it all together perfectly. The column on the right is all about accuracy. How far is your arrow from the bullseye, from that true estimand? That's your error and your bias. The column on the left is all about precision. How tightly clustered are your shots with each other? That's your deviation and your variance. They are related, but they are very distinct sources of problems.
So all of this just begs the question, how do we build the perfect estimator? I mean, one with absolutely zero bias and the lowest possible variance. It sounds kind of impossible, right? But there's a beautiful mathematical concept designed to do just that. It's called the U statistic. The U in U statistic stands for unbiased, and the logic behind it is just pure elegance. To get the most stable, most reliable estimate you possibly can, you don't just apply your utility function to your data once. No, you apply it to every single possible combination of data points in your sample. By averaging across all of these combinations, you essentially cancel out all the random noise, and you're left with the clearest possible signal of your model's true performance.
And this brings us to the big payoff. Remember that concordance indicator we talked about, the one that checks if pairs of things are in the right order? And remember how we restricted it to only compare positive examples to negative ones? Well, when you take that exact utility function and you apply the U statistic logic to it, that is, you calculate it for every single positive-negative pair in your data and then average all the results, you have just derived from first principles the area under the ROC curve, or AUC, one of the most robust and widely used metrics in all of machine learning.
So here is the crucial takeaway from all of this. There is no single perfect score for an AI. Every metric, whether it's accuracy, AUC, or something totally different, is just an estimator for a different ideal. Understanding these building blocks, from the simple Heaviside function all the way to the elegant U statistic, empowers you. It lets you move past the simple question of, is this model good? And start asking the much more powerful question, what do I truly value in this model's performance, and which estimator is going to help me measure it?